In this video, we will be learning how to find zeros of polynomials. First, we must recall the rational zeros theorem. This theorem states that for a polynomial in standard form, all rational zeros must have the form p over q, where p is a factor of a naught, the constant term, and q is a factor of a sub n, which is the coefficient of the leading term in the polynomial. All rational zeros must be a combination of the factor of a naught over factor of a sub n. We can find all rational zeros of this form. Let's look at an example. If p of x is equal to x to the third plus 3x squared minus 4, we can use our factor of a naught over factor of a sub n to find all potential rational zeros of this polynomial. In this example, a naught is negative 4, the constant term, and a sub n is 1, which is the coefficient of the leading term in the polynomial. The factors of negative 4 are plus or minus 1, plus or minus 2, and plus or minus 4, and the factors of 1 are plus or minus 1. To find the possible rational zeros, we need to take each of the factors of a naught and divide them by each of the factors of a sub n. Simplifying, we get plus or minus 1, plus or minus 2, and plus or minus 4. Now these are all of the potential zeros for the polynomial, but if we note, the degree of the polynomial is 3, so we can have at most 3 zeros. So some of these are not actual zeros of the polynomial. In order to determine which are the actual zeros of the polynomial, we need to plug these values into the function and see which ones give us 0. So let's find the actual rational zeros of this polynomial p of x. First, let's plug in negative 1. Simplifying, we see that it is not equal to 0. And as we go through these quickly, we find that we have 2 zeros, 1 and negative 2. These are our rational zeros of this polynomial. Now, to find factors from our zeros, we get these terms, x minus 1 and x plus 2. These must be factors of our polynomial p. So now we can take the factors that we have and FOIL them to get x squared plus x minus 2. And the reason we're doing this is because we haven't completely factored our polynomial yet. If we have these two factors, we're still missing a term. So in order to find it, we're going to FOIL, and then we're going to divide our polynomial by this product. For long division with polynomials, we need to find what we can multiply that x squared term by to get our x to the third term. And first we will put in a placeholder for our x term in our dividend. So here we go, we're going to multiply by x. We get this product. Now we'll do some subtraction to get 2x squared plus 2x. Bring down the 4. And then if we multiply by 2, we get this product, 2x squared plus 2x minus 4, and we see that our remainder is 0, which is good. That means it factors evenly. So our fully factored form of p of x is x minus 1 times x plus 2 quantity squared. So the multiplicity of the x plus 2 factor is 2, and this is good because it gives us a degree of 3, and we knew already that we could only have 2 potential factors, x minus 1 and x plus 2, so this just shows us that the x plus 2 has a multiplicity of 2 in our fully factored form. Let's look at another example. If we have the polynomial p of x equals x to the fourth minus 5x to the third minus 5x squared plus 23x plus 10, and we want to find the possible rational zeros of this, we start in the same way as the previous example. We have to look at all of our potential combinations of a factor of a naught over a factor of a sub n. In this case, a naught is 10 and a sub n is 1. So we've got potential factors of 10 are plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. And then our factors of 1 are just plus or minus 1. Now we have to do all of our combinations, and then simplifying we see we get plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. So we have 8 potential zeros of this polynomial. Now we need to go through and see which ones are actual zeros by doing some quick calculations. And we see that we have 2 rational zeros of this polynomial, one at -2 and one at 5. So now, using what we've factored, we have x plus 2 and x minus 5. And what's left is x squared minus 2x minus 1. Since that doesn't factor, let's recall our discriminant to see if there is a solution to this quadratic. Our discriminant is b squared minus 4ac. In this case, we have -2 squared minus 4 times 1 times -1. This gives us 8, which is greater than 0, which means there are 2 distinct solutions to that quadratic. Now, they're not going to be rational numbers, they're going to be real numbers, but we can still find them using the quadratic formula. Plugging in and simplifying, we get 1 plus or minus root 2 as the solution to that quadratic. These are our final 2 zeros. 1 plus root 2 and 1 minus root 2. Now let's look at all of the zeros of our polynomial. We have our 2 rational, 5 and -2, and we have 2 irrational, 1 plus root 2 and 1 minus root 2. These can be estimated as at 2.4 and minus 0.4. Now, to graph P, let's begin by plotting our zeros. -4, -0.4, -2 and -0.4, and 2.4 and 5. Now our end behavior, we have an even power and a positive lead coefficient. What that tells us is that y will go to positive infinity as x goes to negative infinity, and y will go to positive infinity as x goes to positive infinity. Basically, the end behavior both will be pointing up as we go out to negative infinity and positive infinity. We also need to note that since we have 4 zeros and the degree of our polynomial is 4, the multiplicity of each term will be 1, so there will be no bouncing. We'll go straight through each zero. Now I think we're ready to graph. And we keep our graph nice and smooth, and there's a graph of P of x.